Good evening. Welcome to lecture 11. So before I start, today I've uploaded a new home assignment. I don't know if you've seen that. So you have time, so you almost have 2 weeks time. So until Sunday next week. This time only 4 exercises, a bit less, so enough time, not too many exercises, but still better to start early, right? To have a look at the exercises. So for one of the exercises, you need next week's lecture, but all of the other exercises you can already start working on after today's lecture. Okay, good. And also, like the grades for the quiz are already uploaded. In case, please check it. In case there's something suspicious, you have the feeling that the grades are not correct or something like that, just let me know, then we can double check. But I mean, typically you should more or less know what is the correct score, right? Just double check your entered grade, whether everything is correct. Good. Then we can start with today's lecture. So we continue with more or less what we have started on working last time. Last time was about barrier option pricing, which is some kind of exotic option. So we continue in this way by deviating from the standard call option, European option, kind of boring thing into more and by looking into more interesting types of options. So last time it was about barrier option pricing, and the thing we have seen was like some kind of closed form solution for barrier options and also some kind of PDE formulation for barrier option. And the technique we were applying was the reflection principle. So today we will not talk about barrier option pricing, but about options that are called Asian options. And then we try to distinguish between different types of Asian options. So I mean, in the case of barrier options, we started in a similar way by talking about what are different types of options. In that case, it were like knock-in, knock-out options, different types of barriers, and so on. So similar today, we talk about Asian options and what types of Asian options exist. And we will see that mainly 2 different types, geometric and arithmetic Asian options. So we will talk about them first in order, first about geometric and then arithmetic options. For geometric options, we will derive a closed form solution. For arithmetic, it's not possible to derive a closed form solution. I will explain why. But for both formulations, we can derive a PDE formulation. And for arithmetic Asian options, the situation is a bit more complicated. Even though they look easier, but the situation is a bit more complicated. So we will derive a PDE formulation and then apply some method. This is called a Rogers-Shih method in order to simplify the PDE. Because the PDE is like has a higher dimension than what you have seen so far because we have a path dependence. So we need to augment the state space in order to account for path dependence. And then in the Rogers-Shih method, it's exactly about simplifying the state space, reducing the dimension of the PDE again to get easier, more tractable solutions. Okay, and then the end, as usual, right, as in the case of barrier options, some parity relation. Good. So Asian options. Okay, so what we have seen so far was like some type where we started with was European options. So if I talk about call options, this means what we had was a payoff function of this type, right? And then we were talking as well about American options. If I specify it to a call option, then it would be, I replace the fixed time t by some time tau, which can be any time before maturity. So this would be the payoff. Tau would be something like the exercise time, right? And today we are talking about Asian options. And Asian calls would correspond to AT minus K, the positive part. And AT is some type of average. Average of option prices over the time period from 0 to t. Okay, so instead of just looking at one point in time, which is either the maturity or some intermediate time, what we are doing for Asian options is really looking at the average price of the stock value of the underlying over some period. So I just adapted it by saying just, okay, from 0 to maturity t. So these are some kind of average options. So you're really looking at at the average, and when the average is larger than the strike k, then you're getting some positive payoff. So that's the idea of Asian options. And about the naming, just if you're curious, why European, why American, why Asian? So Asian just because they were traded for the first time in Tokyo, at the Tokyo Stock Exchange. So that's where the name comes from. For American options, it's not the same, right? It's not because they were traded for the first time in America. Maybe this is the case, but I don't know, right? It's more because to distinguish it from European, because America used to be the land of freedom. I don't know if it's anymore, right? But I mean, there's more degrees of freedom in American options than European options. So because you can decide on when to exercise, that's where the naming comes from. Okay, and then we have Asian options. I think it's just some kind of pun compared to American and European options. Okay, and then, so the situation is that we want to talk about this average option pricing. And then the question is how to compute the average. And I mean, if I would ask you to compute the average of a couple of values, what you probably would do is just to compute something like the empirical, you would call it average, but what you are doing is you compute the arithmetic average. That's not the only way. You could also compute the geometric average. So the difference would be, so the arithmetic average, if we have two values, it would just be like, I sum them up and divide by 2. Right? If I have n values, I sum them up, divide by n. The geometric average works in a similar way. But instead of adding, I multiply. So I have something like x1 times x2. And now I do not divide by 2, but I just take the square root, so to the power 1 over 2. If I have n factors, then I consider the product of the n factors and take everything to the nth root, so 1 over n. Okay, so these are the two objects we could consider for averaging. Both are pretty similar, typically, right? So they lead to similar values, to different values, but to similar values. We talk about the advantages of the two approaches because mathematically, clearly, these are different operations, have different properties, but empirically, again, they lead to very similar values. So this means more or less you can interchange the outcomes. And then, I mean, in practice, what you would do if you wanted to compute the average value, you need to specify the times for which you extract the asset values, which you take in order to compute the average value. So this means you would, I don't know, consider a time period over 1 month, and every day you would consider some asset value, and then you would have 30 observations and compute the average value. This would be a discrete average. In contrast, if you increase the frequency, and let's say you go over to every hour, every minute, every microsecond, and so on, so you would consider something like the continuous average in the limit. So decrease the time period, the time delta, and then in the limit you consider, I mean, the continuous time limit, and this leads then to some notion of continuous averaging. Of course, in practice, it's very difficult to do that. You cannot observe continuously. But I mean, if we do that, then we get, the hope is at least that we get some kind of nice solution. Because our framework, the Black-Scholes equation and everything, you know, Black-Scholes framework is in continuous time. Very often we see that if we have these continuous time considerations, we get closed form solutions. So it might be nicer to consider the continuous average as an approximation for high frequent observation, let's say. Okay, so we talk about this difference as well, and then there are different notions of how the strike can be defined. So something like you fix some number, that's what I've written down here, some k, that's a fixed strike, or you could have some floating strike. This means the strike itself depends on an acid value. Good. So these are the different types of averaging. So there's arithmetic, there's geometric, there's discrete observation, and there's continuous observation. So this means in total we have 4 different types of how AT can be defined, so the average. So the first is, I guess the naive approach to averaging values. So you have n observations, you just take the arithmetic average of them, 1 over m, n times the sum over the STIs. Okay, that's discretely sampled arithmetic averaging. And what you should have in mind for this is you really have some times, t1, t2, and so on, until tn. And the difference between ti plus 1 and ti is constant. So we have, typically you would observe every day, not like after 2 days and then after 4 days or something like that. So typically the difference between the observation dates is constant. And if we have n of them, this would be capital T over n, because the last observation typically would be t, right? Okay, so we have n over them, so we have something like a grid of times, and the distance between the time points is t over n. And this means this object here, the arithmetic average, is also something. Here I could also, I smuggle in like t over t here. So this means, and you see here I have then t over n times 1 over t. So this means I can also write this as 1 over t times the sum, same sum as before, times STI, and what I have then is times t over n. T over n is just ti plus 1 minus ti. Okay. Now I was talking about the continuous time limit, and in order to come from the discrete case to the continuous time limit, what I do is I decrease the size of ti plus 1 minus ti. So the delta t gets smaller and smaller. And if I do that and look at the sum, what happens is that this object converges against the integral. You've seen that before, right? So this means in the limit means delta t goes to 0. So I call this delta t. I get 1 over t. Nothing happens to 1 over t. Integral from 0 to t, s u du. Or maybe to avoid confusion, I should call this small t. Okay, and then we have what is standing here. So then we have the continuously sampled arithmetic average. So that's really how you see that the discrete case is consistent with the continuous case I've written down here. Good. So that's the first way to define an average. And the second way would be to consider geometric averaging. Okay, geometric averaging is what is standing here. So I just consider the product of the acid values I observe and take everything to the power 1 over n. If I do this, so I have st1 times until stn to the power 1 over n. And this is the same as e to the power log of the same thing. A logarithm of a power is just, I can write it as a factor in front of it. So I get this the same as e to the power 1 over n, and here I have still the logarithm. Okay, I do it slowly, step by step, until stn. Here I have logarithm of the product. This becomes sum of the logarithms. So I really get e to the power 1 over m, n times the sum from 1 to n times the logarithm of STIs. Just 2 times logarithm rules applied. Okay, and this is what is standing here. And now I apply the same logic that I have explained here when I was switching from discrete time to continuous time, taking the limit of delta t going to 0. I see that this integral converges against exactly what is standing below, right? So delta, no, too small, delta t going to 0, I get this object, just this object here, converging against 1 over t, integral from 0 to t, logarithm of st dt. Okay, and then I have exactly what is standing here. So this is the continuously sampled geometric average. And now, if you look at the objects, and remember what we were talking about last lecture, we were talking about barrier option pricing, and there I explained, I motivated a lot what we did, right? I was talking about applying the logarithm, considering the log prices, and try to explain that log prices are easier to deal with. And here's a similar situation. So you look at the arithmetic average, and you see we are integrating over prices, ST. In the second situation, geometric averaging, we are integrating over log prices. Again, similar consideration. The second situation is easier because we are talking about log prices. And this will later lead to the case that we can solve the second case explicitly, but not the first case. Okay, you might ask, why are we considering geometric averaging? But that's the reason, more or less, in the Black-Scholes model. Okay, and so this was averaging, and then we can also consider different notions of strikes. So the standard case would be just have a fixed strike, as explained earlier. So this just, we're just considering really like a standard European call option, replace the asset price with the average asset price, and then you get a fixed strike call option, fixed strike put option in the Asian case. Floating strike means you take something like a European call option, and then the strike of the European call option depends on the average value itself. So it's also some kind of notion of averaging of an Asian option, but related also to the asset price, right? So this is just really like, you can start really with a European call option, European put option, and just that the strike is not fixed, but is k times the average price. And k, the small k here, is not like an absolute value, but something like a percentage value. Right? You see this? Typically, ST is on the same scale as AT, right? And k, the small k in front of the average price, is just some multiplier of the average value. Something like, I don't know, could be 90% of the average value or something like that. Okay, that's floating strike and fixed strike. So we start talking about fixed strike and come back to floating strike later, but they are kind of similar to deal with when you want to compute the values. Okay, so here, an easy example. So we have today's stock price is 100. This means we are starting here. And then we observe, like, every month some stock value. So the first, 1 month, 2 months, 3 months. And the values we observe are 98 maybe, and then 102, and then 103. Okay, and then we observe a we observe, or we want to price some, or consider at least some Asian call option, strike 100. Good. So this means what we need to do, we need to compute the average value. So the average is something like after one time step, it's 98. After two time step, it's 100. After three time steps, it's 101, right? So this means in the end, we end up slightly above the strike, and the final payoff of the option is 1. Okay. So the question would be, why do we need these types of options? Why are they interesting? Is this again some object thought of by mathematicians, or is there really some use in these options? Okay, and there are really some situations where these options are not only for speculation, but really have a couple of advantages. And I mean, the average value operation, so take the average value of a couple of stock prices, is something which is kind of robust. This means the variance of the operation is reduced by a lot. If you think of just some random evolution of stock prices, so similar to what I have drawn before, you start here and then observe a lot of stock prices like this. I don't know, this is kind of random what I draw here, and then compute the average. This smooths a lot the operation, so you will get something which is much smoother than the red dots here, much less volatile, and so this means this is kind of robust, even if the price increases or jumps or something like that. This leads to the average value only to increase a bit, not to make a huge jump immediately, because I mean the effect on the average value of one outlier is quite small. So the volatility is reduced. This can be desired. I mean, one effect of that is that it's more difficult to manipulate the outcome 80, the average value, because I mean, if you want to, manipulation, I mean, for stock prices is quite difficult, of course, but not impossible. But there are a couple of historical situations where prices have been manipulated. I don't know if you've heard about the LIBOR scandal, interest rates, right? When different banks communicated the interest rates and so on, and just manipulated the prices in favor of what they wanted to. And something like this is super difficult if you have to manipulate a lot of prices instead of just one price, right? So this is more robust against price manipulation, and on top of that, it's less volatile, right? So this means if you think about the pricing of call options, we have talked about the vega, the Greek letter vega, which is referring to the derivative of the call option price with respect to volatility. I've explained, the larger the volatility, the more expensive an option is, because you have more chances to get very high outcomes in the end. The less volatile an option is, the cheaper the option becomes. This means Asian options are typically cheaper than European options, simply because they are less volatile. There are less chances of very high outcomes in the end. This means this reduces in the end the price, because you're covered against losses. So because they are less volatile. That's the reason. Another situation would be that, just a use case to illustrate, and it can be really reasonable to trade them. Think about FX trading, so foreign exchange market. For example, you frequently trade or do business from the point of view of some company in a foreign country. So, for example, company in Singapore doing trades with, Chinese, in the Chinese market, doing regular payments in China. So this means what happens is that, the books and everything of the company are in Sing dollar, but what the company has to pay will be in renminbi, right? So this means let's say the payments are regular payments every month or something like that. And if you need to pay every month something like 100 renminbi, so what you actually need to pay needs to be converted into Sing dollar. Right? This is relevant for you if your company is in Singapore. So this means you multiply with STI, and STI would be something like, in that case, the exchange rate Sing dollar over renminbi, right? At time TI. So 100 is in yuan, and then you multiply with this conversion rate, something right, 0.2 or something, I guess, right? And then you get what you actually need to pay in Sing dollar. Okay, and you do this over like every month. Let's say n could be 12, then you're looking 12 months, 1 year ahead. These are your payments. And of course, your largest concern is that the exchange rate changes so that your payments become more expensive. This is your concern, which you want to hedge. So this is upside risk, so to say, and what you want to do is you want to profit from increasing prices on the same scale that you need to pay more for your payment. So this means what you could do after what you have learned in this lecture is to invest in a call option. Then you would profit from increasing prices in a linear way. So you think of some call option exactly on this payment stream. This means something like K times, and here I could include the N as well. Let's say 100. Okay, and so this type of call option is what you're interested in. I could also write K times N times 100 as 1K, but this just, doesn't matter. Okay, and I can also or let's say, okay, let's maybe do it this way for sake of notation. And now you see if you really invest in, let's say, 1 over, maybe now I see 100 times n is better, because if you now invest in 1 over n times 100 of them, then what you get is exactly the what I want to get is something like some type of Asian option. So this would be 1 over n times 100. So I start with sum from 1 to n like STI, and in order to get this, I need to multiply in front of that with 100, and so this is not the right thing to do, minus K, and this only is correct if I start differently, right? So 100 minus K 100 times n, right? So this means what I need to have in the end. So this is where I started from, what I explained, and this is just convention. This would be my corresponding strike. I'm looking at some K tilde, and this is correct, right? So I'm just multiplying the first sum with 1 over n times n. And the second difference, I have K times 100 times n. So this means this is the same payoff as 100 times n payoffs of Asian options. Okay, And now you may ask, why should we invest in something like that and not rather in call options every month? Right? And the answer, according to my third bullet point, would be it's cheaper to do that. It's less volatile, you save a lot of money, and if you're really running a business on a large scale, this may make a difference, right? You're just saving transaction costs as well. You're having the operational advantage of having less volatility. You're saving also option prices on top of transaction costs, so you're saving a lot of money. And that's the reason why something like that might be beneficial for you to do. So sorry for, I think this is now the correct thing. So the 100 times STI refers to the, just to clarify this refers to the value in domestic currency, right? If you do your payments in a foreign currency, this would be the value in domestic currency. And then in the end, you're just really looking at Asian call options or Asian options on the exchange rate itself. So this is the exchange rate, the FX rate. Okay. Yeah, and now we are looking at the price. So later we will see how to compute this chart exactly. But given you can compute it, you will get a curve like this. And you see two things, right? First of all, if we compare the payoff of call prices, European call prices with Asian call prices, what we see is first the European call option is more expensive. This is exactly due to what I have explained. We have more volatility for European call options. Therefore, Asian call options are cheaper. And what we also see, it's very hard to distinguish the yellow and the orange line at all. So this means the geometric average and the arithmetic average are really very close to each other. So it doesn't matter too much which method you choose in the end for averaging. The outcome is very similar. And this is a motivation to just choose that method that leads to a nicer formula in the end. Okay, so what we will do today is we are looking for solutions for the continuous case, for the continuously sampled Asian option case. Because the other case is a bit trickier to treat. The continuously sampled case is just a very nice theoretical object we can cover with methods from stochastic analysis. So as you will see, the arithmetic Asian option case, so the one where we just take the integral over the asset prices, is more difficult to treat. And the reason, again, is because, asset prices itself are not so nice as compared to log asset prices. They are nicer, and therefore we can find a solution for a geometric Asian option case. Okay, so we start with the nice case, with the geometric averaging case. So in that case, we define first the geometric average. This is our object GT, as I've explained earlier. So you start with the product of the STIs, 1 to the power 1 over n, and consider the limit of time differences going to 0, and you get a geometric average in the limit. Good. And I just define a couple of objects to make the calculations easier. So xt is the exponent here, and therefore gt is e to the power xt. And therefore what I want to compute is something like a call option on gt, and gt is e to the power xt. Okay, that's my payoff, and correspondingly I want to compute the price of this option. And if you want to compute the price of such an option, as I've explained a couple of times, the naive approach is always to start with risk-neutral valuation. So you start discounting the value, the payoff, and then computing the expected value. So that's what we want to do. And we have seen in the last lecture that the log value of SU, here I consider 2 times u and t. It's just r minus sigma squared half times u plus sigma times w plus logarithm of S0, right? I forgot the initial value. But you see, if you take the differences at 2 times, SU and ST, the initial value doesn't matter, cancels out. It's the same for both, and you get this difference you see here on the right-hand side. So in particular, what is nice is that this depends only up to all the other components, which are deterministic, on the increment of the Brownian motion. The increment of the Brownian motion is independent of everything before that. That's a very nice property. We make use of that. Okay, so let's start computing things. So again, what we want to compute is an option on e to the power xt, and therefore we start computing xt. Okay, xt is the integral over the log prices, and now we want to compute everything at time t. Okay. The payoff, gt, depends, however, not only on future values, but also on what has happened until time small t already. So the integral is from 0 to capital T. So this includes values of the past that already have occurred. It's a bit different compared to European options, right, where you just look at some future value. Here, really, you're standing at time small t, and things that have happened before have an influence on the future value of the payoff. Okay, and now what we do is we just separate the integral into 2 parts. The first part is what has happened before, and the second part is what lies in the future. So what has happened before is something we know, right? Some known deterministic value, given the information until that time, and everything else lies in the future. It's random in that sense. Okay, so mathematically, I just split the integral from 0 to small t and then to an integral from small t to capital T. The meaning is really that the first object is known at time t, and the second object is random. Random means lies in the future. Okay. Good, and now I see that, first I perform a similar trick as the one I did before. I smuggle in some small t divided by t. I multiply with 1 in that sense. And what I achieve is I get t divided by capital T. And if you look at the definition of xt, you see now I have the x with the index small t just standing here, because the x with the small t is just 1 over small t, which is standing here. So maybe to make it clear, I use 2 different colors. So here I divide by blue, by the blue t, and then you see this object, 1 over t, is just my xt. Okay, and the second object, the 1 over t, here I'm integrating over future log asset prices, log SU. Okay, and now what I can do is I use simply this representation that we have discussed on the previous slide, and I just this allows me to start with the value log of st and everything else that comes thereafter. In particular, all of these quantities are deterministic. These are not problems. Log of st is deterministic, and the only thing of bit of concern is the increment of the Brownian motion. When I start from time t and time u wanders, time u becomes increasing, I integrate over u. So this is the only thing I need to compute. Okay, it's not straightforward, but we can do that, as we will see. Okay, let's talk about the other objects first. So, I mean, here, log of st, if I integrate over u, this is just a constant value. I can write it in front of the integral and integrate from t to small t. So maybe I write it out. So if I have integral t to capital T log st du, this is just the same as capital T minus small t times the logarithm of st. Right? And this is what is standing here. And here for the second object, I'm not integrating yet. I'm just writing things down. And this is the third component I have. Good. Okay. Well, so I'm continuing with the second time integral. So du integrated over u minus t. Well, I mean, this is just integration with respect to the identity, more or less. So I'm just getting a square. I need to divide by 2. So I get 2 over t, evaluate at the boundaries, capital T and small t. So I'm just getting capital T minus small t squared divided by 2. And of course, here the same coefficient as before, still here. Okay, and the thing of concern that might be a bit more difficult to compute is this integral. Okay, and so we want to understand this integral. So we're integrating more or less over Brownian motion or over increments of the Brownian motions, and we try to understand what the value is. But actually, we don't need to compute the exact value. What we actually are interested in, because we want to compute the expected value of this, is really like the distribution of this object, because then we can evaluate the integral. That's all we need to know, just the distribution. The precise value is not so interesting. It's really the distribution, because in the end, we want to compute the expected value of that. Okay. So the goal will be, I mean, the other quantities are all known to us. We really want to understand what is the distribution of this object. Okay, and here's the answer. So this object we want to find the distribution of has, in the end, a normal distribution with a variance t minus t to the power 3 divided by 3. So that's the thing we want to have. If we have that, then we can combine the things and evaluate the integral. Okay, how can we see that? So there are 2 ways to see that. I start with the brute force method, I'd say. So I'm just looking at the integral. I'm thinking of the definitions you have learned about in lecture 3 and lecture 4, right? How to discretize an integral, how an integral is defined. Okay, well, this is a bit nasty. I mean, you've seen a couple of these calculations, but in the end, this works, right? If you want to evaluate an integral, it's a bit nasty to do that, but you can always break it down to the definition and then try to simplify things, and maybe it works. So that's what I'm doing here. So, I mean, according to the definition, I mean, here the approximation symbol just means if the difference between if the partition is fine enough. So if the difference between tk plus 1 and tk is small enough, then the right-hand side approximates the left-hand side. Okay, so this means I'm starting with some partition of the time interval from t to capital T. Okay, and this is just a definition of the integral. And I mean, now I'm just looking at what is standing there, and I'm considering all the factors in there separately. So I have wtk times tk plus 1. I have minus wtk times tk. And then I have wt times tk plus 1 and also wt times tk. And now I claim this is the same as this one. Okay, why is this? This is simply because what we actually have is here the sum from 0 to n minus 1 of Wt times tk plus 1 minus tk. Okay, and the index is k, so if you look at the summand, the Wt does not depend on k, right? So this means I can write this in front of the sum, so I get Wt times the sum. From 0 to n minus 1 over the times tk plus 1 minus tk. Okay, and now I'm summing over just the differences of time. So this means the first summand would be Tn minus T0, and the second one would be plus T0 minus T1. You see T1 is appearing twice, once with a minus sign, once with a plus sign, cancels out, and so on and so on. So in the end, it's a telescoping sum. So you just get the last value minus the first value. So this would be the same as Wt times Tn minus 1 plus 1. So this is Tn minus the first value is T0. And the argument here is this is a telescoping sum. Scoping sum. Okay, and Tn is just T, and T0 is T. So I get just Wt times capital T minus small t. This is why I have here Wt times capital T minus small t. Okay. Okay, it's just looking at a definition so far. And now, now you need to, either you have a good intuition for that or feeling, or have you done a lot of these types of exercises. The question is, what do you want to achieve by looking at the definition? And the hope is a bit that we can transform this integral into some other type of integral that we can better understand. So here, we have started with a du integral. What we very often can better understand is an integral over a Brownian motion. Because then we know it has nice properties. The expected value is 0 and these kind of things. You can apply Ito isometry. I don't know. There are a couple of things you can do. But if you have the Brownian motion as an integrand, it's not that easy. So it's, you really want to integrate with respect to the Brownian motion. And therefore, the hope is somehow that you can transform the object you have here into an integral of a Brownian motion. So if you peek a bit and take a look at the last line, you see you will have something like differences of the Brownian motion. So you want to achieve something like that. Okay, and now if you look at your at the object you have here, this is not exactly what is standing here. So here you have the Brownian motion, here you have the Brownian motion, but they have the same index. So in order to achieve the decomposition you see in the last line, what you actually want to do is something like not have the same indices in the two sums. And there's a simple way to achieve this. Just switch the index of one of the sums. Okay, and we do that for the first sum first. So this means here in the second line, the summation starts from 0. So that means the first summand is Wt0. In the second line, still, the first summand is Wt0, but we start a summation from 1. Right? So we start this summation index with 1, but we still consider, of course, the same object. We achieve this by reducing the index in the sum by 1. And the same, of course, for t. It's the same thing, we just need to reduce it. And the upper limit is not changed, so this means this is not completely correct unless we add it manually after the sum. Okay, here this sum should have the same indices as the first sum, so this means we also want to sum from 1 to n minus 1. So this means we separate the first index here, Wt0, T0. Okay, and this means in the next step what we want to do is we want to combine these two sums together and obtain something that we can transform to an integral in the end. So this is what we have here, right? Here I can write the two sums from the line above into one sum. And now you see what happens is that I really have some kind of differences of two Brownian motions here. Okay, and what about the other summons? So here I was just writing Wt times capital T minus Wt times T. And I mean, I'm again looking at the definition of the partition and see that my Wt0 times T0 is actually the same thing as Wt times T, because T0 is the same as small t. So this means these two objects, they cancel out. And what I have here, Wtn minus 1 times Tn is just Wtn minus 1 times capital T. So this means I can write this together, both have the factor capital T here and here, write this as capital T times the difference of Wtn minus 1 and Wt. Okay, I'm almost there where I want to be. I just need to realize that two things. So actually in the first sum, the difference of the Brownian motion, the increment of the Brownian motion is not in right order, because I want to have the larger time index of the Brownian motion first. So this means I need to multiply this with minus 1. Then I get exactly what I want to have. And second, I can apply the same telescoping sum trick as before, again to this difference. Okay, so this means, and then I get summation from, I mean, here k minus 1 to n minus 1 as an upper bound. K minus 1 because the first index would be T0, which is exactly Wt k minus 1 for k starting at 1. So this is telescoping sum, the argument we apply here. Okay, and then I have the two times the same sums, the same indices. Here I can combine them and write them together. So I really obtain some kind of object that looks a bit nicer, because it has the meaning of, if I consider again, the delta t going to 0 as some integration over a Brownian motion, according to what you have learned in the first part of the semester. Okay, so this means if I let delta t go to 0, I get really this kind of object on the, here I'm not yet letting delta t go to 0. I do this in a later step. So what I have shown first is that the integral on the left-hand side, this is the one we started with, is approximately the object on the right-hand side. Okay, and again, this can be understood as some kind of integral with respect to the Brownian motion, but what we at least have, even if you don't consider the integral notation, is that we are summing over increments of the Brownian motion. And this is very nice, because increments of the Brownian motion are beautiful objects. You know the distribution, they are independent, we understand them very nicely, so we can directly write down a distribution of them. Okay, so I do this step by step. So what we have here on the right-hand side is, again, the sum of increments of the Brownian motion. So we know that first, increments of the Brownian motion are independent. Second, increments of the Brownian motion are normally distributed, so Gaussian. And third, if we look now at the object we have here, the sum over them is just a sum according to 1 and 2. A sum over independent normal distributions. The sum of independent normal distributions is again a normal distribution. Sum of independent normal distributions is normal. Okay. And this means the object on the right-hand side is normal. So what we have here is normally distributed with some mean mu and sigma. And the question is, what is mu and what is sigma? Okay, these are the next steps. So we know it's normally distributed, and next steps are really to determine the only two parameters that we need to know, because this is everything you need to know about normal distribution. Once you know the mean and the variance, then you know everything. And maybe I'm better using, there are two competing notations, so it should be sigma square here, right? Just to be consistent with everything else in this lecture. Good. And now let's compute first the mean. For the mean, you can either compute the mean of the left-hand side or the right-hand side. If you compute the mean of the integral, it's very clear. You can just, interchange the two integrals. There are a couple of mathematical arguments that back up this operation here. No worries. And you have expected value of an increment of Brownian motion. The increment of Brownian motion has a normal distribution, and the mean of that is 0. So the expected value of an increment is 0. If you would compute the expected value of the right-hand side, more or less with the same argument, you get expected value of the increments is 0. So the expected value is really 0. So we can already answer the first question, mu is 0. Check. The second question is, what is the variance? Okay. And we start by computing the variance of the right-hand side. So we have the variance of the sum from 1 to n minus 1 of these increments of the Brownian motion, tk minus 1 times capital T minus tk. Okay. Now you know variance of a sum is actually, if you want to compute the variance of x1 plus x2, let's say, then it would be the variance of x1 plus the variance of x2. But you also have to take into account the covariance, so you have something like 2 times the covariance of x1, x2. Okay, and similar here, right? So this means what we get is we get the sum of the variances of what we have here, t minus tk. And here we get also something like a sum over, I don't write it down, covariances of something. But this is 0 simply because the increments are independent. Right? So this means all the covariance terms become 0. If you consider the covariance of two independent random variables, the covariance will always be 0. The other way is not correct, right? The covariance being 0 does not imply independence, but if you have two objects that are independent, the covariance is always 0. So this is 0 because of independence. independence of increments. Good. So this means we just have to deal with the sum over the variances. And now I can, still a sum from 1 to n minus 1. And here the t minus tk, I can write it in front of the variance. So I get t minus tk squared times the variance of wtk minus wtk minus 1. The variance of that is just, we know the distribution of increments, right? It's a normal distribution, and the variance is just the increment in time. So this means the variance here, this is just tk minus tk minus 1. Okay. And this means what I have here does correspond to a summation of t minus tk squared, and here I have the increment in the time component. So this is, again, I'm having here this approximation argument. Difference in times is very small, so now I want to switch to the integral. So this means this is approximately the same as the integration from 0 to t of t minus u times, and here I have the time increments, so this means here I'm integrating over u. T minus capital U, so this is corresponding to this component, and the integration over u is corresponding to the increments in time. Okay, it's just definition of the integral. And this is easy. This is something I can compute. And I should start my integration not from 0, but from small t. Okay, I'm integrating t minus u squared. I'm actually just integrating the square. I have a minus sign in front of it, so I get this to the power 3 with a minus sign in front of it divided by 3. So this is the same as minus t minus u to the power 3 divided by 3, evaluated at the boundaries. So to make this clear, so the variable is u, so the upper boundary would be u being capital T, the lower one u being small t. This is, and then I get, this is just, the upper bound just gives me a 0, and the lower bound gives me t minus small t to the power 3 divided by 3. So this is the variance of the object. And this is exactly what I was claiming earlier, that this is the variance of the normal distribution, right? This is what was standing here. Okay, and after a short break, you will see another way to compute the same thing. Okay. So what we just did was actually to compute not the integral directly, right? But like what we did was to determine the distribution of this object. Again, just to make sure that we all know where we are. So what we actually want to do is to compute this expected value. Expected value involves, k is fixed, involves gt. Gt is defined as e to the power xt, right? Gt as e to the power xt. So actually, we want to compute the distribution of xt in order to be able to compute this expected value. And we have simplified the xt in this way, and we see, okay, we can compute everything up to this expression. And so what we did in the next step was to simplify this expression to understand the distribution of this integral. And here we saw the distribution of this integral is a normal distribution. This was what we have computed in this quite lengthy calculation. And I mean, this is not very nice. You can do that, and you need to, you need to understand, you need to look at the indices, to play around with the indices and so on, and then maybe you see, okay, it makes sense to transform it to increments of the Brownian motion, and then you can compute the distribution. Okay, but there's also a nicer way to see to do that. I mean, what we actually want to compute is the distribution of exactly this integral. So the integral from t to capital T, wu minus wt du. And I mean, the second part, wt, is just fixed over all time steps u. It doesn't change, right? So this means if I write it down, this would be the same as the integral over using linearity of the integral, wu du minus wt times capital T minus t. So the only thing I want to compute is the wu du component. Okay. And now, I mean, every time you want to do some kind of stochastic analysis, to compute things and so on, what you always should have in your toolbox is ethos lemma, right? So this is one of the first things. And how does it make sense here to apply ethos lemma? So, well, ethos lemma tells you if you apply it, you get a certain expression. You get derivatives and so on. You get some dt terms. You get some dwt terms. And so what you might want to achieve is that this expression pops up after some application of ethos lemma. And now we know what ethos lemma tells us. In front of the dt term, there is the derivative of the function with respect to time. So we hope that this would be something like, so that's very heuristic. After ito, this should be some kind of integral df d, yeah, let's say du. So the question is, what is f? So that we can apply ethos lemma. What is f such that after deriving with respect to time, we get the Brownian motion? Someone see it directly? Okay, I mean, the solution is not very complicated. I just define f t wt as t times wt. Then the derivative of this with respect to time gives me just the Brownian motion. Right? So this means what I have is that an application of ethos lemma tells me dwt times t, same as, okay, if I define f in this way, the same as df wt. So first derivative with respect to time, so I get wt dt plus derivative with respect to the Brownian motion, so t dwt. And here I have exactly what I wanted to have on the right-hand side, right? I have exactly my integral on the right-hand side. So I write it out in terms of integrals, the SDE. And I have that wt times t is the same as wt times t with the small letter plus the integral from t to capital T du plus integration from t to capital T u dwu. Okay, it's just the same as the line above in integral notation. Okay, and now you see what I want to achieve. I want to have actually the left-hand side. So I want to have the left-hand side also derived from the equation I have here after applying Ito. This means I want to bring the integral over the Brownian motion to the left-hand side. And you see what I need to do. I need to subtract exactly what is standing here. So wt times capital T minus t. Okay. So I have t wu, maybe I do it slowly, minus wt times capital T minus t is the same. So this is what I want to have here actually. It's the same as w capital T times t. So I start on the left-hand side of the line above, minus wt capital T minus t integral to capital T u du, and now I need to subtract also this, minus wt capital T. So just to make clear what I have done. So these two quantities are the same, so I've just subtracted them. Then I have started with this equation, have put it to the left-hand side, and I have just subtracted this on the right-hand side, and also, with this equation here with the minus sign on the right-hand side, and this here, right? Okay, just to make it clear. Good, and on the left-hand side, I then obtain the integral I want to have, so wu minus wt du. This is the same. This is exactly the line I have explained above. And here you see there are a couple of things that simplify. For example, this term here gets cancelled out with this term. Right? Once it's appearing with a minus sign and once with a plus sign. Okay, so we just obtain wt times capital T. Here we also have a multiplication with the capital T. So I have w capital T minus w small t times capital T minus integration over u dwu from t to capital T. And here this is just integration over the constant value capital T with respect to the Brownian motion. So this means what I have on the right-hand side is just t minus u integrated with respect to the Brownian motion. Okay. This means this is probably a more elegant way to solve this problem, right? Of course, you first need to step back and then get this solution on the right-hand side. Well, I did not solve it entirely because, you still need to compute the distribution of this thing on the right-hand side. But now this becomes much easier because I mean, we directly see the expected value is 0. So you get expected value of the object on the left-hand side. It's just the expected value of the object on the right-hand side, which is 0, because this is a martingale. And for the variance, the variance is defined as the expected value of the squared expression minus the squared value of the expected value. The expected value is 0. So this means the variance is just the expected value of the squared expression. So the variance is the same as the expected value of the integral t minus u dwu squared. Simply because the expected value is 0, so minus 0 squared is still 0. So this is the only thing I need to compute. And now I can apply, again, nice properties of the integral with respect to the Brownian motion. One of them is the E2 isometry. And the E2 isometry tells me I can write this also as integral over t minus u squared du. And this here is E2 isometry. Okay, and actually this is no more random. After applying the E2 isometry, I get rid of the Brownian motion, and I don't need to apply the expected value anymore. I only need to evaluate this integral. I have done this before. This becomes t minus small t to the power 3 divided by 3. Okay, again, I think this is the more elegant, the nicer solution compared to the previous one. But yeah, this is up to you how you solve something like that. But in the end, what we get is we have a normal distribution, expected value is 0, and the variance is what is standing here, t minus t to the power 3 divided by 3. Okay, so we're coming back to our original problem. So we wanted to compute the distribution of xt. So all of this is, so the first part is like, this is deterministic. This can be considered as some kind of drift we have here, right? So this is deterministic. I mean, it's not deterministic, but it's like, yeah, deterministic is maybe too strong. It's known at time t, right? This value. Known at time t. And so this means if we want to model the distribution of x capital T, we have the known component and the unknown component. And now we have computed the distribution of this object. And this object has, again, a normal distribution, mean 0, and variance t minus t to the power 3 divided by 3. This is what we have computed. Good. I can split this part into components, let's say, 1, 2, here I have 3, and here I have number 4. So number 4 is the random component. I give number 3 the name mu bar. So this is my component number 3. And here I just say the component number 4 has a distribution with variance. I mean, I just need to consider the variance of the integral and multiply it with what is standing in front of it to get the corresponding variance of the whole object. And if I'm talking about the standard deviation, of course, I need to take the square root. So I get the square root of the object number 4. So this is standard deviation of 4. Yeah. And this means in total what I have is I have object number 1, I have object number 2, I have object number 3, and I have object number 4 that can be modeled in this way. Okay, and I mean, I can also write number 4 simply by saying I know the standard deviation, just by this definition, my sigma bar, and I can define a distribution in a way by saying, okay, if I multiply a standard normal distribution with sigma bar, I get the corresponding distribution that I have here. It's the same thing in terms of distributions. It's exactly the same. I just need to scale a standard normal distribution with some standard deviation. Good, so this is my xt in terms of all the components which are incorporated in xt. And again, what I want to compute is not xt, but actually gt, which is e to the power xt. Xt is consisting of these 4 components. So I have e to the power, that's the first component, that's the second component, and here I have 3 and 4, right? I'm just writing it now in terms of, I mean, originally it was a sum, and now I'm applying the exponential to it, so I get a product of these 4 terms. Good. The first term is, I mean, by definition, it's just gt to the power t divided by capital T. I just interchange the order of xt and t to the power t, and then I can consider t divided by capital T as an exponent of e to the power xt. For the second, very similar, I write the logarithm st in front of the factor, and I get just st to the power what is standing here. And I still have the last component, but okay, it's just some cosmetics I'm doing right now, just writing things a bit nicer. And in the end, what I have is that the value of the geometric Asian call option that I want to compute can be written as the expected value of this expression. So this was what the last half an hour was about, to compute, to express gt in this way. And now we could continue and work the next half an hour, next, I don't know, 40 minutes or something like that on evaluating this integral, but no, I will not do this now. So this is like standard. This is more or less what you have done already a couple of times, what we also did in the last lecture when we were talking about barrier options. I had a similar form, right? You need to integrate with respect to a standard normal distribution, multiply with the PDF, evaluate the integral, and so on. This is quite standard. You also have done this for, I mean, to derive the Black-Scholes formula, standard call option. If you do this, I recommend you to do this as a preparation for the exam, for example, to repeat this argument again, right? Doesn't hurt. And if you do this and then complete the square, evaluate the integral, you get this formula. This looks very much like the Black-Scholes formula. D1 and D2 are different from Black-Scholes, so don't be confused. Again, abuse of notation from my side. But in the end, it's very similar. So the arguments, the techniques are the same, more or less. So once you have an expression of this form that you can express in terms of a standard normal distribution, which we have, right? Because y is a standard normal distribution, then you can compute the integral. You just have to work a bit. I will not do this now, but again, I recommend to do it as an exercise. The solution is here, so to verify your working. Good. Okay, so I guess you believe me. Now, geometric Asian call options are actually quite nice. So the trick here was to switch from the arithmetic formulation, the naive formulation, to the geometric formulation to get rid of the exponential term of the stock price itself, to get a nicer expression. And in the end, it was just evaluating integrals over the Brownian motion, which we can do, right? Evaluating integrals over the stock price is more difficult. Okay, but this is the case for arithmetic options. Okay. For arithmetic options, we therefore don't have explicit pricing formula. So, because what we need to do, again, if we apply this, the same methodology, would be to evaluate some kind of integral st dt. And this is not tractable. This is not possible. And I mean, there are situations when you can do that, but not in, I mean, for special situations. But in general, there's no pricing formula. Okay, so this means for this case, this is, more difficult case. This is good news because this is the more interesting case as well. There we need more advanced techniques to solve it. So we can start by looking at how the PDE changes in that case. So first of all, we need to realize if we want to determine the price at some time small t, often arithmetic option, we need more information than just the current time and the asset value. Because if you think about the payoff we are looking at, it's the average value of all the values, also of all the values that already have happened. So we need to keep track of the path of the underlying security. The current asset value doesn't tell you anything about the historical evolution of the asset prices. But we need information on that because this has an effect, has an influence on the payoff of the Asian option. This means we need to extend the inputs. So not only the time and the asset value matters, but also some IT variable, I call it just IT, which keeps track of the path of the underlying asset. This is information we need to determine the value of the Asian option. Okay, so we have this additional parameter IT, and this is some path-dependent variable, and how we start to define it would be to say, okay, IT could be some integral over some function that depends on the asset values and possibly also on time, and we integrate it over du. So we try to, of course, we cannot include the whole path as a variable, but we want to reduce it to one number that tells us enough about the evolution of the path, and the approach would be to define some kind of integral that does the job. Okay, so this is an integral over time, or this means it's some dt variable. I could also write it as dit is f dt. Okay, so that's the approach. And if we're talking about the Black-Scholes framework, where dst depends on dt and dwt, this means that dit has zero covariation with itself first, because it's just a dt term. Again, dit is just f dt. So in the end, dt squared is 0. And so informally, I could write this as f squared, dt squared. This is heuristically written at 0. dst, so the dt term combined with the f dt, 0, and the dwt with the dt combined is also 0. So here we get also, this is 0. Okay, and then we want to compute the evolution of the price, because we want to apply the usual argument to derive the PDE, which would be to compute the price of the corresponding option and to compare it with the evolution of some investment in the bank account, apply no arbitrage arguments, and derive the PDE. Okay, so for this we need to understand how the price evolves over time. So what is dft when ft denotes the price at some time t? So we apply Ito's lemma, and what we get is, exactly the usual formula, and the additional component we get is the dit terms. So here we have dit term, and here we have dit term. So these are things that are new. If you compare it with lecture 6, where we have done the same kind of argument, then the red terms are not there. They are there because we have now dependence on it. Good. dit, again, is f dt, because it's just an integral over time. dit squared is 0. This is what I have written down on the previous slide. So this is dit squared. This is 0. And dst, dit is also 0. dst squared, again, this is st squared sigma squared dt, because we are in the Black-Scholes model. Okay, I have a couple of dt terms. So here's a dt term, here's a dt term, and here's a dt term. I write them together here in one bracket. I have, I write the dit term separately first. But actually, this is also a dt term, right? So this is also f dt. So I could also write it in the first bracket. And one dst term, which also incorporates one more dt term. Okay, let's continue by the usual argument, which would be to set up some replicating portfolio, which would be self-financing an investment in the asset and in the derivative. So gamma t derivatives and beta t stocks. Same notation. And then we have the value can be written as a weighted sum of the corresponding values weighted with the investment. So gamma times f plus beta times s is the value of the portfolio. And this portfolio is self-financing. So this is the first condition. This is because it's self-financing. So this means the value evolves only changes because of the changes in the underlying instruments, because of dft and dst, but not because we extract or inject any money. So this is this equation you have here. Okay, and then we input just what we have computed on the previous slide. dft is, this is just the purple color dt term from the previous slide. This is this part. And we have gamma t times derivative of f with respect to s dst plus beta t dst. So, compared to the previous slide, we more or less have this additional term. And the typical argument now is to choose beta t in such a way such that we eliminate all randomness. So this means we need to choose beta t to be minus gamma t times the delta. The delta is partial derivative of f with respect to s. And then we see that the dst terms cancel out, and we only have a dt term. And in the dt term, compared to lecture 6, this is kind of the new term. Right? This term was not there in lecture 6. And this is the term which is there because of the dependence on I, because we now have path dependence. So we continue by, exactly as I mentioned, by choosing beta t minus delta times gamma t. Then the dst term becomes 0. So what happens then is the dst is 0. So, and we get that the value of the portfolio evolves deterministically over a short period of time. So if we only look a short period of time in the future, then we see that we know how the value of the portfolio evolves according to this equation. And now we compare the investment with an investment in the bank account. And what we would do with the investment in the bank account is to invest the value of our portfolio just at the risk-free rate. Then that investment, the evolution of the value of that investment would be RVT dt if the value of that investment in the bank account would be, at first we consider the case where the bank account investment would give us a higher value change. Then what we would do is to invest as much as we can in the bank account, while at the same time we sell our portfolio value. We sell and get VT, invested in the bank account. So that's a zero trade first, and the value change over time is positive. So this is arbitrage. In the same way, if the bank account investment would give us a smaller value increase, then we would borrow money of size VT in order to invest everything in the portfolio. So that's the argument you have heard already a couple of times, I think, but it's always nice. And this explains that dVT needs to be RVT dt, roughly. So no arbitrage. Could also just write down in a very brief way, say no arbitrage. No arbitrage explains dVT being RVT dt. And now you just need to put things together. Vt is the value of the portfolio that I have defined earlier. Beta t is defined as minus gamma t times delta. This is how I have defined it earlier in order to get rid of the dst terms. Now on the right-hand side, I have the 2 times gamma. So this means this is something like gamma t times ft minus delta ds st. And I can solve this now for gamma t. You see, then I get this is the investment in the derivative. Okay, and then I plug everything back in equation 1, which was this equation. So this means now I have computed my gamma t. I plug this in back. I compare the coefficients. And I mean, what you get in the end is this PDE. So it's exactly the same argument as in lecture 6. And I mean, because it's exactly the same argument, we get almost the same result. And if you think about what we did, the only thing that was different was this part. So this means also we get almost the same PDE. The only thing that is different is this part. So this is, I just write down U, right? So you know what I mean is that this is the only change compared to lecture 6. Just one additional component in the dt term. This explains you directly how the PDE changes. Okay, so this means we understand how the PDE changes for arithmetic options. The question now is how to choose f. How to choose, in the definition of IT, the corresponding integrand f, such that the PDE makes sense. So if you think about the PDE, what we need to have is in the end, I mean, the PDE describes the evolution of the value over time. So IT should fulfill two things. It should give us enough information at time small t, and in particular at the boundary condition, so this means at the time of the payoff, it should give us enough information to be able to define the payoff. Right? So this should be some random variable from which I can infer the payoff of the option, because I need to be able to define the boundary conditions in the end. And for this, I need information, in this case, on the arithmetic average of the asset prices. Good. So I want to, in other words, I want to choose IT such that at time capital T, I can define AT from it. Good. So this means at maturity, IT needs to contain all information at about AT. Otherwise, I cannot define the boundary conditions. Okay. Again, I start with the naive approach, so to say. I just say, okay, well, I integrate over asset prices, ST. This means in that situation, IT would be 1 over, no, I don't have, yeah, that's the point, right? So IT would be just like an integral from 0 to t over the asset values. This means you see already what I need to do at maturity. I need to divide by capital T in order to get the average value. In other words, if I look at this equation, IT being the integral, this means dit is just st dt. And then I choose, just in the PDE, I have, I mean, here you see this just df di times f. And now I have chosen my small f to be the asset value itself. So if I plug this in, I just get a multiplication with the value s. So this is my f. I've chosen here. And this is a valid choice. I can define my boundary conditions. I get all the information I need. I can define a PDE in this way. This works. For the terminal condition, again, what I need to do is I have the relation that AT is I divided by T. So in the formulations of the different combinations of floating and fixed, you just need to divide I by T in order to replicate AT. So this is the case here, 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 and here. Okay, so these are the terminal conditions. But I want to emphasize this is not the only possibility. Again, all you need to do is to define some integrand such that you have enough information to define your boundary conditions in the end. And this is also possible in a different way. I could also choose f in such a way such that at all times t, it is the same as at. So in other words, it is the same as the integral over from 0 to t over some function f that depends on time and on. I denote the time by u now as u du. And this should be the same as 1 over t integral from 0 to t s u du. This is my at. So this is what I want to have. Okay. Because then, by definition, at terminal time capital T, they are the same. So this information is definitely enough to define the boundary conditions. But the question is, what is my f in this case? Okay, so I can also write at as 1 over t times yt. And yt is just, if you look at the definition of at, then it's clear. It's just the integral from 0 to t s u du. And, solution, as so often in this lecture, is just Ito if you want to determine f, because you need to get some dt term. And for this for this kind of question, we start on the left-hand side. Dat should be something dt, because I want to show this is f, and this is exactly what I'm looking for. And for this, a straightforward approach is just to apply Ito. So I have this representation for at. I'm applying Ito. So I have dat. First, I have the derivative of this expression with respect to t. So I'm getting minus yt divided by t squared dt. Then I get the derivative with respect to y, which is 1 divided by t dyt. Okay. Yt divided by t is at. So this means the first term is the same as minus at divided by t dt. The second term involves dyt. Dyt is st dt. So I have here plus 1 divided by t times st dt. Now I'm just need to put things together, and I get st minus at t dt. This means in the end, my f can, if I choose f in this way, I can just integrate over this this integrand, and I get some integral that always has the same value as the average value, without multiplying it by 1 over t. Okay, this means I can choose my f in this way, and then, if I plug it in, I have that first of all, that A is at all times A t is it. So previously I had here an expression of the form df di, but now I have at is it, so I can just replace it by a in this situation because a is I, and this is my f, right? So if you compare this with the PDE we have derived earlier, first you can replace I by a, which is nicer because you understand a, it's just the average value, and I mean f can be replaced by s minus a divided by t. Okay, another advantage of this formulation is that it's a bit easier to formulate the boundary condition, or boundary conditions in the 4 cases, because you don't have to divide by t anything. It's just you can you can define everything in dependence of a, right? Directly use the variable a because this is exactly your I you want to use. Also, your function value is always doesn't depend on I, but depends on a in the end. Okay, but I mean, both formulations are correct and completely fine, completely correct. And you can, I mean, there are probably many more formulations that work similarly. Just all you need to have is enough information in order to define your problem. Okay, let's do a short break and then continue with the simplification of this problem. Okay, so we've started talking about the arithmetic Asian option, and yeah, the situation is not as nice as in the geometric Asian option case. So without showing it to you, I hope you believe me, it's more difficult to compute the integral over asset prices than over log asset prices, and therefore we switched to the PDE formulation. For the PDE formulation, the thing that changes is exactly this component, so some additional dependence on some path-dependent variable, which either can be AT itself or some IT that is some kind of integral over asset values, right? That's an approach that's very often used for path-dependent derivatives. Good, and now this equation to solve it is a bit inconvenient. I don't know how familiar you are with numerics of PDEs. Probably you're learning about it, right? So finite differences and so on. So if dimensions are too large of PDEs, it's very difficult to solve them. So it would be nice to simplify this equation. So even dimension 3, which we have here, I mean, you can solve it. But it's better to have something two-dimensional typically. So dimension 4 is already highly problematic. Dimension 3 sometimes is okay. So here we have dimension 3, but dimension 2 would be definitely better than dimension 3. So, so we have the PDE that involves 3 components, 3 partial derivatives, 3 dependencies, T, S, and some I. And the question would be, can we simplify it? Can we somehow replace, I mean, time, we cannot get rid of time, but can we replace ST and IT by something else that incorporates information of both and transforms the PDE into something that depends only on 2 variables? So can we reduce the dimension by 1? That's the question. Okay, and so we look at the payoff we are talking about. We are talking about the payoff of an arithmetic call option. And by definition, this is just what is standing here. So it's the, I mean, up to discounting, this is exactly the value. So the conditionally expected value of the payoff can be written in this form. And now I'm doing the same kind of consideration that I've already started with when I was talking about geometric Asian option case. So I'm splitting the integral into a component that depends on everything until time t. So this is the component which is known. So this is the second component in this case. So this is known at time t and something that lies in the future values. And the problem with the integration over asset prices is that, I mean, the dependency, the asset value at some future time SU depends on not only on the value itself, but also on all the values before that, right? So the value of the Brownian motion at some future time depends on all the values before that. But if I switch to, so I mean, we have that SU, I mean, you know how it is defined. It is defined as S0 times E. Here I'm in the risk neutral case. So R minus 1/2 sigma squared times U plus sigma times WU. And the Brownian motion component here is the problem because I don't have an increment of a Brownian motion, but I just have like the Brownian motion itself. So, and this also depends on S0. But if I just consider S0 divided by ST, what I get rid of the S0, right? I get something like e to the power R minus 1/2 sigma squared times U minus T. So U is now a larger time than T plus sigma times the increment of the Brownian motion. So this is independent of everything before time t. So the thing becomes nicer if I divide by st. When I divide everything by st, of course, in order to make this an equation, I need to multiply everything also with st. Yeah. st is known at time t, so I can write it in front of the expected value. And this has the advantage that this is really some random variable, this part here, future, random, and somehow independent of history. Right? And I achieved this by division with st. And the rest, the component here, I give this a name. If I multiply it with st, I give this a name xt. So xt by definition, if you look at this, would be k minus, so this is my average value. So I could also write k minus, so this is not really my at, but something like the integral, so the path-dependent variable divided by capital T divided by st. So this tells you something about the ratio of your current asset value, st, in comparison to the average price. So, you could also write this in a deterministic way as some function depending on st divided by at, so the ratio between the asset value and the average value. So this is really the idea that you set the current value of the asset price in relation to the average value, and this is kind of the transformation we are looking into. So it's enough to know the ratio of the asset price compared to the average value. You don't need to know both variables in the end. This is the hope, that we can transform our equation into something that contains enough information, so the variable xt, and xt is one dimension smaller than st and it combined. And on top of that, this seems to be a good object if I look at this transformation, because information on xt at time t seems to be enough to define the payoff at time t. Okay, that's the motivation. That's how we start. So why did we do that? That's just a summary of what I explained on the previous slide. So if we have 2 times u being larger than t, if we divide by st, we get an object that is independent of the history. So su divided by st is independent of the history. So the expected value we consider is really something that depends not on any previous values. We don't need any additional information. We can treat this as some purely random thing, and which only depends on xt and, of course, the time t, because the time t defines the length of this integration, right? Okay, so on these 2 parameters, so it seems to be some kind of dimension reduction. So we define our function h, that is now a function of x and time t, as what I have defined here on the previous slide. So this would be my h up to discounting. So this is what I want to define as my function h depending on x. And if I discount this value and multiply it with s, I get exactly the value of the derivative. So the price of at time t of the Asian call option can be also written as s times h. And h depends only on x and t. And what I need to achieve is to get rid somehow of the s. But this is a nice shape, right? I just need to multiply everything with s, and then I obtain my option value, my option price. Okay, and the next step would be to plug this in the PDE and to see whether things really simplify, because PDEs are kind of, very often things are, if you just have this multiplicative structure, things simplify when you consider derivatives. Okay, so we do that. So we have the PDE for the Asian arithmetic option, which we have seen has this form. So here I'm choosing f to be s. I could also choose it differently, as we have seen, but here I choose it to be s. S being f. And this is my definition of the variable xt that we have seen on the previous slide. So some function actually. I call it a transformation, but actually you can consider x as a function of I and s. So consider x as a function of all that is standing there, so of s and I. I mean, capital T and k are fixed numbers. Okay, and if I have x and consider this as a function of s and I can consider the next step, because what I want to do is I want to plug this into the PDE. I want to see what happens if I do this kind of transformation. So I need to see how x depends on the variables that are involved in the PDE. So what is the derivative of x on s? So what is the partial derivative of x with respect to s? So here I have the shape of x, the derivative of x with respect to s. I mean, I have k minus it over t divided by st. So I get minus k minus it over t divided by st squared, right? I take the derivative with respect to the denominator, minus st squared. So I can write this as the original quantity with minus sign divided by st. So this is what I have here. And maybe I should omit the small t just to make it clear that what happens if I input the corresponding numbers. So minus I. Okay, minus x divided by s. And similarly, when I consider the derivative of x with respect to I mean, k is just a constant value. So what I get is just minus, I mean, what is standing here? Minus 1 over t divided by s. Okay. And now we exactly do what I explained. So we have this structure. F is just s times h. We want to plug this in the PDE. X is defined in this way. And now we need to compute how the derivatives of f relate to like this product structure on the left-hand side when I compute the corresponding derivatives of that. So we start by just going through all the derivatives involved in the PDE. So we have the time dependence first. I mean, on the left-hand side, we have the derivative of f with respect to t. On the right-hand side, we consider derivative of s times h with respect to t. I mean, s does not depend on the time, so we just get s times h with respect to t, right? It's just a linear dependence here. Okay, the next object is the derivative of f with respect to s. Okay, at first sight it looks like, I mean, only s depends on s, but h doesn't. But I mean, x is defined independence of s. So both factors depend on s actually. And we need to apply the product rule and chain rule to compute that. So this means what we get is df ds is the same as, and then we apply the product rule. So the derivative of s with respect to s is 1. So we just get h plus s times the derivative of h with respect to s, which is I apply the chain rule, derivative of h with respect to x times the derivative of x with respect to s. Good, and derivative of x with respect to s is what I have computed here. So this is minus x over s. So this is the same as h plus s times the derivative of h with respect to x times minus x divided by s. And now you see the s cancels out here, and I get h minus x times dh dx. And this is what is standing here. Then I continue with the second derivative, because this is also involved in the PDE, right? I'm now looking at this quantity. So second derivative of f with respect to s. And in order to compute this, I just need to derive the df ds quantity from the left-hand side, which I've computed here, once more with respect to s. So again, h depends on s through the dependence on x. So what I get is dh dx times dx ds minus, and here again the product rule. So I have minus dx ds times dh dx minus x times the second derivative of h with respect to well, so this is not completely correct. So here I consider dx times dx ds. So you see the first two summands, they cancel out. They are the same. And the second one, here I have dx over ds. This is again the quantity I've computed here, which is minus x divided by s. It is the same as minus x times the second derivative of h with respect to x times minus x divided by s. So I get minus times minus, so plus x squared. So this is x squared divided by s times second derivative of h with respect to x. But this is the same what is standing here. Then I have the dependence on I. Okay, s does not depend on I, but h does. So I have df di would be s times the derivative of h with respect to x times dx di. Dx di is something we have computed here. It's minus 1 over t divided by s. This is s times dh dx times minus 1 over t divided by s. So you see the s cancels out, and I just get minus 1 over t times dh over dx. So this is what is standing here. Okay. Just a lot of chain rule, a lot of product rule. I don't know, yeah. Okay, this is, but anyways, this, I mean, this looks a bit boring, but this, I mean, what we actually did is quite interesting, because we are in the middle of transforming this equation, this PDE, into another one that depends only on x. So we have transformed these PDEs, these partial derivatives, into partial derivatives that depend only on x and t on the right-hand side. And now what we do is we plug in just the right-hand sides of these equalities into the PDE. We can do that. And then, I mean, when you do that, I mean, you plug in the first equation, for example, you have the dependence on t, which is s times h dt. You get something like s times dh over dt. And so on, and so on. So in total, you get this PDE, which is standing here, times s. If you plug this in. I didn't write this down, but in the end, you get s times something. S is positive, so you can also divide by s. And this is very nice. This is beautiful because we get rid of s in this way. So the PDE does not depend on s anymore. I mean, you can simplify what you get here a bit, I guess, if I see this correctly. For example, the RH here. So you see RH here and here, positive and minus sign. You can cancel out, and you can simplify the PDE even further a bit. But in the end, what matters is that this PDE only depends on 2 variables instead of 3, as before. So in the end, we get this PDE depending only on 2 variables, x and t. We need to pay a little price for that, which is that the solution domain now ranges from minus infinity until plus infinity. Because if you look at the definition of x, so x is defined as k minus it divided by t over s. IT is the integral. It starts from 0. It can become as large, it's unbounded, right? So if the second term is, smaller than k, then it's positive. Otherwise, it's negative. So it really ranges from minus infinity until plus infinity. So there are no natural bounds for that. This is a small price we have to pay for that, but we get a PDE that only depends on 2 variables. Now we look at the terminal conditions. So what happens at maturity? This is the payoff we are looking at. This is the payoff of an arithmetic Asian option, I over capital T. So I is the integral over the asset prices. By definition, X is defined as K minus IT divided by T divided by ST. That is the definition we had here. So if I multiply this with S, you see what you get is that this just is K minus IT divided by T. If I multiply this with an additional minus sign, I just get I over T minus K. So this here is the same as S times minus X. Yeah? By definition of X. And then S is always positive. Contains only positive values. These are asset prices, right, in a geometric Brownian motion, always positive. So when I apply the maximum of some value and 0, I can also write this in front of this operation. So this is what I'm doing on the right-hand side. So I write just the asset price in front of it. Okay, so S times minus X. And you see, this is very nice because the terminal condition now has exactly the shape we are needing. Right? Because we are looking at F, which has the form S times H. So this was what we were starting. So how we were starting. So this was S times H X T. This was our decomposition. And now we are looking at the right-hand side and we identify, okay, in that case, H needs to be the positive part of minus X. Good. Okay, and now we can continue a bit. We have the PDE, we could stop here, okay, this is fine. But we can, the thing that is a bit troublesome, I'd say, is that the unbounded solution domain. And so what we can do is we can look at 2 cases that can happen now. The 2 cases are X can be smaller or equal than 0 or larger than 0. And a bit counterintuitively, I would say, X being smaller or equal than 0 is the good case now. Okay, what does it mean, X being smaller or equal than 0? So again, we look at the definition of X. So X being smaller or equal than 0 just means that X at time small t being smaller or equal than 0, the denominator S doesn't matter, right? It's being smaller or equal than 0, it does not depend on S. If I divide by something positive, this doesn't change the sign. So this just means that K minus IT divided by capital T is smaller or equal than 0. This just means equivalently that IT is greater or equal than K times capital T. Okay, what does this mean? Let me just illustrate this. IT is this integral over the asset values, okay? And here we are looking at the time on the x-axis, so we're starting at 0. And here we are looking at the values of IT. And at time 0, the value of IT is always 0, right? IT is an integral over asset values. If we integrate over nothing, the initial value is 0. And then as time progresses, we integrate over positive value, IT increases. It's an increasing function of time. So the value would look somehow like this. I don't know, So it never decreases, somehow always increases, depending on how S evolves. So this would be IT, how it evolves. So this is my IT. And now I'm looking at hitting the boundary k times t. So let's say k times t is somewhere here. K times t. So this means there exists the case, this is here, that IT is greater or equal than KT. And this corresponds exactly to the situation. So X, maybe I just omitted the time index here. So this corresponds to the situation X being smaller or equal than 0, and this corresponds to the case X being larger than 0. Right, so we always start in the case X being larger than 0, and at some point, IT may become larger than k times t. This also might not happen, but if it happens, then we stay in that region after that time. That's what we are talking about. And this is indeed the nice situation. Why is this a nice situation? Okay, let's look at this case a bit further. So we have 2 times S being larger than t. Then, of course, I mean, IS is larger than IT. Right? Again, the integral is an increasing function, so therefore I at a later time needs to be larger than I at the previous time. So this means if xt is smaller or equal than 0, and we are looking at ss times xs, by definition of x, this is just k minus is divided by t, because x is just the same thing as on the right-hand side divided by s. Okay, and S is larger than IT, so this means minus IS is smaller or equal than minus IT. So I get this inequality from, so actually here, it's even a strict inequality. And the right-hand side is ST times XT, which is smaller or equal than 0, because we are in the case that XT is smaller or equal than 0. This means, in particular, that I get, if I divide by SS, that XS is smaller or equal than 0. It's just what you directly see from the figure, right? That once I'm in the case XT being smaller or equal than 0, I'm staying in that case forever because the integral is increasing. So, okay, we have this chain of inequalities. And this means if xt is smaller or equal than 0, I have that this difference that I have here, so this is positive, of course, the first part, the integral, because I'm integrating over something which is positive. A quotient of 2 asset prices cannot be negative. And minus xs is also positive. So I have just a sum of 2 things which are positive. If xt is smaller or equal than 0, then minus xs is also positive. And this difference is positive for all future times s. But this means if I'm looking at h, which is defined in this way, according to what we have seen earlier, this part is always larger than 0, right? So this means the positive part here is not necessary. It doesn't change the thing. The maximum of this part and 0 is always the first part, right? It's always larger than 0. This means I can just omit the positive part, and now I'm in a situation where I can compute this expected value. This is very nice, right? I mean, the positive part function is nonlinear, and this makes the computation difficult, but if it's not there, I can compute things. Good. Let's do this. So here I'm considering this expected value. What I'm doing in the next step is just, again, interchanging the 2 integrals, so the expected value and the integration over time. And then I'm getting integration over the expected value of this quotient, SU over ST. And here the value XT, this is known at time t, right? We've seen this already a couple of times today. And so therefore, actually, if I want to compute the conditional expected value of that, it's just no computation necessary because this is just considered to be a known value at time t. Okay, so I'm just multiplying this with the discount factor in front of the whole thing. And now I need to compute this expected value, and here I don't need to compute anything actually, because I mean, I know that the asset price is a discounted asset price is a martingale, right? What this actually means is that SU, so U is a larger time index than T. And the martingale property just means that e to the power minus RU times SU is the same as e to the power minus RT ST. So this is the martingale property. So we have seen that e to the power minus RT ST is a Q martingale. Yeah, we've discussed this in lecture 7 or 8, was one of the exercises, and this is more or less the property, the martingale property. So this means if you condition on the previous time t, you just get the current value. That's the martingale property. And I mean, now I'm just reformulating this equation, and this is the same as to say that the expected value of SU divided by ST is e to the power R times, so I'm multiplying with e to the power minus R times U, then I'm getting e to the power R U minus T. This is the expected value. And this is what is standing here. So I'm not using any properties of the geometric Brownian motion or nothing like that. I'm just using the martingale property, actually, in order to get this. And this is nice, right? So I got rid of the ST dependence and so on. So I just need to integrate over an exponential function. But I mean, integrating over an exponential function is something you know how to do since high school. It's very easy, so nothing changes. I mean, here we have a coefficient in the exponent. It's r, so we get an additional 1 over r when we integrate, but that's all. And when we do the integration, so we really get the same function, but just with 1 over r, we evaluate at the boundaries. That's all. If we evaluate, I mean, you see we have the exponent once with positive sign, once with a negative sign, so we get 1 when we evaluate, and minus what is standing here for the lower bound. Okay, but that's all right. So we can really compute the corresponding expected value. It's very, very easy in that situation, and that's the, as I mentioned, the nice case. So x being smaller or equal than 0 is a nice case, because and the main argument here is really that we can get rid of this positive part function. Good, and so we are not completely done, so we just need to combine the calculation with our case. So what we have computed was actually the h part, so we need to multiply it with s in order to get the value. So the second part, the h, is exactly from the previous slide, and if we multiply it with s, what happens is, I mean, happens nothing to the first part. This is exactly what is standing here, and then for the second part, we are just using the definition of x. So x again is just I divided by t minus k divided by s with a minus sign, right? So k minus, sorry, it's k minus I divided by t. So here we have a minus sign, and here we get a positive sign, and we just we multiply it with s, and we get rid of the denominator and get I divided by t minus k. We get a closed form solution for this case. Okay, how can we use that? Because, I mean, it's a bit hard to distinguish the two cases, so, I mean, we really want to combine them. We also want to solve the problem in the case x being larger than 0. Because, you know, if you think about this case, what I've told you is that we always start in the case x being larger than 0. This means this is the important case. If I sell you an option today at time 0, I'm in the case x being larger than 0. So I need to know about this case as well. It can happen that after some time, I'm switching to the case x being smaller or equal than 0, but I'm always initially in the case x being larger than 0. So I also need to consider that case. But I want to make use of the information about the other case as well. Okay, let's do this. So for this case, there's no explicit solution, and now we have understood why this is the case, because we have this positive part in the expected value of a nasty integral, which we cannot, at least not easily evaluate. Okay, but we know in this case that we can solve the problem via PDE. The PDE actually is defined on the whole solution domain, which ranges from -infinity until +infinity. But now we have additional information about what happens for negative values. For negative values, we can solve the thing. We don't need to solve the PDE, but we directly know the value. So this means actually we only need to solve it for positive values. And then once we switch to negative values, we can directly use the formula. And we can also use the formula for the case x being smaller or equal than 0 to define the boundary conditions at 0. So that's the idea. Okay, so this means in the case x being larger than 0, we know this is the PDE. This is what I have derived earlier. The reduction to 2 dimensions, to 1 space dimension, 1 time dimension. Then we know what happens if we make the transition to the case x being smaller or equal than 0. So if we plug in x being 0, then we get this explicit formula. So this is just using the case x being smaller or equal than 0 and plug in x being 0, because this includes exactly this case. And then we need to define what happens at the boundary +infinity and what happens at terminal time. Okay, for this we need to look at the definition of h. So h was defined in this way. What happens if x goes to infinity is that I'm subtracting infinity from the integral, right? So this means I'm integrating over something in the first component, I'm subtracting infinity, I take the positive part of that. This is as small as it can get, infinitely small, minus infinity. Positive part of that would be 0. So I'm just having the expected value of 0, which is 0. Okay, let me write this down. So this is just like the expected value of the integral t to t su st du minus infinity, right? Positive part. So, okay. This is just, it's not very precise, not very rigorous. It's of course a limit consideration, but you see what happens if I choose very large values of x, is that this can never be positive. This is what I'm trying to say. So this becomes 0. And here for this case, what happens in that situation is that I'm looking for h at the integral from capital T to capital T, su st du minus xt, positive part. So here, the first part is, of course, then 0. So I'm integrating over, no domain. So this is just no integration. So this is 0. And x is positive because we're in the case x being larger than 0. So again, I'm not being positive, so negative, and taking the positive part function. This is 0. So this is 0 as well. So we have the two boundary conditions, which both are 0. So we can reduce the solution domain. We have reduced the solution dimension. So this is a very nice formulation now that we can solve. The only drawback is a bit that we lose a bit of explainability because we are now talking about x and not about AT and S itself, but apart from that, I mean, numerically, this is a nicer formulation. Okay, the last part of today's lecture is about, I mean, similar to the last lecture, about parity relations, which we also have in the case of Asian options. So the definitions we are talking about are IT, the integral, over the asset prices, and AT just being like the average value, or like just 1 over T times IT. Okay, and for fixed strike arithmetic Asian options, I mean, the payoffs are just the ones I defined earlier, just like the ones of European call options, put options, where you replace the ST with the AT, and AT again is I divided by T. Good. And I mean, the logic of the parity relation is more or less always the same. You combine the payoffs of put and call options and relate them to something that is more or less independent of the put and call options, and then you try to evaluate all of the quantities involved here. So if we look at, formally, this means if we look at the relation, the difference between call and put options in the Asian case, but again, I mean, the shape of the arguments is exactly the same as in the European case. You just need to look what happens if you subtract the payoffs. And what happens is, I mean, here, again, there are two situations. So either the first component is positive, let's just do it verbally, right? If the first component is positive, then the second is negative. This means in that situation, what is standing here is just IT over T minus K. In that situation, the equality is correct. In the situation that the first component is negative, the second component is positive. But I have a minus sign in front of that. This also makes the equation match the right-hand side. So you just need to look at the two cases which are there. It's always the same kind of argument. Right? We have seen this in the last lecture. You have seen this in the lecture on the put-call parity. For call options, it's this kind of argument. So we have this relation between put and call options. And now we know that the value of the left-hand side is just the value of the difference of the values of a call and a put option. And in order to determine the value of the right-hand side, we need to apply risk-neutral valuation. So we need to compute the value of this object here. But this, in the end, is just the same kind of calculation that we did on this slide. It's exactly the same. Because then there's no positive part anymore on the right-hand side. We just need to integrate over the asset values, and this is something you can do. So the right-hand side can be computed as before. And if you compute it, these are the values we have computed, right? So this is what you get if you do the calculations for the right-hand side. And then in the end, you get that the put-call parity can be just written in this explicit form. Okay. I mean, that's quite a lot for today. So basically everything about Asian options you can talk about. In particular, we have seen the difference between geometric and arithmetic Asian options. For geometric Asian options, situation is a bit nicer. We get an explicit solutions, which we don't get for arithmetic Asian options. But we were able to improve the situation a lot by reducing the dimension, and in the end also reducing the solution domain with this Rogers-Shih method, right? Okay, stop here, and that's it.